a thin gap between two parallel flat plates in horizontal, and make a little hole in the center of one of the plates. Let's investigate the flow in such a cell if a different liquid is injected. First, I'll go to the theoretical formulation, then the experiments, and the comparison between the theory and the experiments, followed by a conclusion. First, I would like to show a few examples of the phenomena that we could get with our data. Here we have water displacing oil. Here we have ink displacing ink with different dyes. And water displacing glycerin. Capillarity is the ability of a fluid to flow in narrow spaces. It's caused by the adhesive forces and cohesive forces. And we can calculate the height of a meniscus by with the liquid air surface tension, the contact angle, that is this angle right here, the density of the fluid, and the radius of the tube. Now we can talk about surface tension. In the interior of the liquid, the molecules have a lower energy than in the boundary because they have more neighbors than the ion in the bulk liquid. So the number, in order for us to minimize the energy, we need to minimize the number of external molecules. So this minimizes the surface area. And we can calculate the shape in the fluid between a thin gap with a surface tension and capillarity, and we have the shape of a meniscus, as you can see from this simulation. Here between the two plates, and here when we have a small droplet between these two plates. Diffusion. One can look at this phenomena and think about diffusion. But why isn't this the phenomena we are studying? We can calculate the type of the diffusion in these parallel plates. Diffusion is the result of the run amok of the particles, and they are self-propelled by the thermal energy. The diffusion flux is proportional to the minus gradient of the concentration and the diffusion coefficient, and is given by this formula, where this D is the diffusion coefficient and phi is the concentration. First, we can calculate the diffusion time with water and glycerin, with 10% of glycerin in water. This time is around 2.49 minutes, and with 20% it's 3.14 minutes around. The error is around 0.2 minutes. And when the liquids are not miscible, there is no mixing between the fluids. Now we can talk about the viscosity of the liquids. Viscosity is the fluid property by which it occurs resistant to shear stress. Shear stress is given by this formula, where μ is the viscosity coefficient, u is the velocity, and y is one of the coordinates. The physical reagents are the intermolecular forces and the transfer of molecular momentum. Here we can draw a profile of velocity when we apply a force in the upper plate when we have a viscous liquid between two plates. And now we can apply the Navier-Stokes equation for us to solve the flow. In a general way, we have this equation, where ρ is the density, v is the velocity, p is the pressure, and c is the stress test, and f is the density of force per unit of mass. And for non-compressible Newtonian fluids, we have that this term is this one related to the viscosity. From the Navier-Stokes law, we can conclude that when the fluid is non-compressible and viscous and is in a Stokes law, we have that the velocity is proportional to 1 divided by μ. That is, it's inversely proportional to the viscosity coefficient. And from from this we can have two situations. When a more viscous fluid is injected, that we will analyze, and when a less viscous fluid is injected. And this is the second case. For the first case, the inner fluids move with a lower velocity than the other one. So there is no instability in the boundary, and the pattern is circular because it's energetically favorable for the pattern to stay symmetrical. Here you can see a picture of us applying oil in water, and here is the final shape, circular. And the distance between the plates were equal to 1 millimeter and a temperature of 25 Celsius degrees. And in the second case, when a less viscous fluid is injected, the inner fluid moves with a higher velocity than the other one. So this causes an instability in the interface between the two fluids. This is called the Safman-Taylor instability. And we analyze this instability further on. And here we can see, I don't know if the contrast is good enough, but we can see when we add water in oil, we have this finger pattern. Herschel flow. This flow happens when we have the Stokes flow between two parallel plates, and the separation is infinitesimal. And here you can have a diagram of this kind of flow. From this you can also derive the formulation, where U is the velocity, P is the pressure, Z is the vertical coordinate, and H is the separation between the plates, and M is the viscosity. This is the velocity derivation from the Navier-Stokes law and the Darcy's law as well. Here we have the continuity equation, and here we have the no penetration boundary in the interface with the air. We can analyze the Safman-Taylor instability, or also known as viscous fingering, and it's a pattern formed in a morphologically unstable interface, and it occurs between two fluids in a porous medium and in a Herschel cell. We analyze the second one. And when the less viscous fluid must be displacing the more viscous, and you can derive the solution for the velocity depending on the separation between the plates and the gradient of pressure. And here we have the incompressible fluid condition. The pattern will be governed by statistical phenomena, mainly the random walk of the particles. The fingers will grow where it is energetically favorable and where the tension is smaller. We have this instability, so we have not a linear boundary. So here we can see the bifurcation of fingers, and the pattern depends on the fluids used, the internal conditions, the initial conditions, the probability distribution, and the final shape will be a fractal. This is a very important parameter. And here we can see in our flow that it does have the shape of fractal. The flow is governed by statistics. We have the fractal behavior, and we can make a comparison of it with crystal formations. And here we have dendritic Cooper crystal in a rock, manganese oxide in a rock, agate inclusions, and here again agate inclusions. And from this you can see that these patterns are very related to each other. And you can also see other interesting phenomena, as well as the bacteria growth. And we have also the random walk, and we have this closely related pattern, as you can see from this figure. And the graph as well, as you can see that the velocity of the tip is linear, as we will see further on our experiment. The random walk is the main cause of the finger shape. Here we have our material that we use for our experimental setup. Here is our setup, and we kept the pressure constant, the syringe. and we evaluated the velocity, the separation, the viscosity, and the miscibility of the fluids. Here we have an illustrative video of air displacing glycerin. We have 2.5 milliliters of air displacing 40 milliliters of glycerin. And here we have water displacing glycerin. As you can see, the finger formation. We can define an experimental parameter, lambda, as the width of a finger divided by the distance to the adjacent finger. And the average lambda was, with oil and water, 2.96, glycerin and water, 1.54, and ink with different dyes, it was 15.69. From this, we can see that the bigger velocity, the viscosity difference, smaller this radio is. We can also calculate the velocity of the fingers against the time. We can see that this velocity follows a linear tendency. This is caused by the constant gradient of pressure. And here we can measure the velocity of the fingers varying the distance between the plates. As you can see, sorry, it's not here, but it's here. It follows a tendency of 1 divided by x. The finger velocity is proportional to the pressure gradient, the distance between the plates, and the viscosity. We can see the velocity follows a linear tendency, and this is in agreement with the equation shown before. In the conclusion, we can have two cases: the known instability, when we have a circular shape, and the Chapman-Taylor instability, when we have a viscous finger impedance. The setup can be approximated to a Herschel because the distance between the plates is much smaller than the length of the plates.
Okay, time's up.
Sorry.
Thank you. And
Here are our references, and thank you for your attention.
Question.
Good morning, ladies and gentlemen. I'd like to ask the reporter for some questions. I'd like to ask you, if you said that there was a high surface tension and you need some pressure, what was the critical flow rate that you need to push into the Herschel cell that you used?
We kept the pressure constant, and then we have a constant gradient of pressure. This is called because we use it.
I just want to ask if you observe some critical flow rate when you push the pressure or in the Herschel cell, when you said that there was a high surface tension.
Yes, there is, but we haven't calculated because it's very difficult to calculate the gradient of pressure inside this kind of cell.
Okay. And I'd like to ask also the shape when there was no instabilities, the shape of the circle. Can you measure the radius of the circle that?
Yes, we can measure the radius depending on the pressure applied and on the liquids used.
Okay. And I'd like to ask the fractals that you observed. How does it change depending on the surface tension?
Well, the surface tension is important because of the instability. If you have different...
I know. I just want to ask if the surface tension will be low or high, how it will change the fractals
if the tension is low, it will be more like a fractal. It will divide more. And if it's very high, it will divide itself.
Yeah, when it will be low, how the fractal will look like?
The same as this, but with a lot of
It will look like the same?
Yes, the general view is the same, but the general shape is the same. But we have more finger divisions, more finger splitting. So it have more fingers.
Thank you.
Okay. Thank you.
First, I'd like to say sorry for the rush plus a lot of time.
Yeah, time management.
For the experimental comparison, I can show you that here, this finger velocity graph, we can see that it follows a linear tendency and with a very small deviation. So we can see from this, and as we applied a constant pressure, and we can see from this that the gradient of pressure will be constant theoretically. So this and the velocities of the fingers are also very close, in a close range. So this is an agreement with our theory that says that the
I want to
velocity.
ask of the comparison with the equations that you use.
We cannot calculate the gradient of pressure in this kind of cell with the equipment we have. So we can compare this qualitatively.
Okay. Okay, I'd like to ask, there was mentioned only the Herschel Flow. Was there any...
Here, it's directly proportional to the gradient of pressure, and if the gradient of pressure is constant, this velocity is constant. So the graph follows a linear tendency.
Okay, I'd like to ask, you mentioned that there was Herschel Flow.
Yes.
Was there any other flow that you observed, or?
There is a Stokes flow between these two parallel plates.
Okay, Stokes flow, and is it laminar or turbulent flow?
For the rate we consider it is laminar, but we can see that variation in the viscosity when they have very low viscosity.
The laminar flow was for every case,
no,
for every experiment.
Let's continue. When they have water, we have a very low viscosity. So this flow probably will be not laminar. But this will not influence shape in our phenomena because we are considering not the small walls of the water and the whole phenomenon itself. The macroscopic phenomenon, not the microscopic.
Okay, and how did you calculate that it's laminar flow?
We can see from our videos. We cannot calculate
Videos?
Yes, the videos.
No theoretical prediction. There was no theoretical prediction for the laminar Stokes flow.
It depends depends a lot on the separation of the plates. If they are very small, it can be approximated to a laminar flow very well.
I didn't quite understand. So now you say that the flow depends on the gap between
yes, it
the
depends
plates.
directly on the gap. Yes, it depends on the gap. And if you have a smaller gap, it will be more like a laminar, and the approximation will be better.
Okay, so you say that when the gap between the two plates is low, then there is a laminar flow.
Yes, it can be approximated to a laminar flow.
Okay. Can you tell me what was the critical flow rate when you said that you observed the critical flow rate? Can you say to me, in your experiment, what was...
The value? No, I cannot.
You said to me,
I said we can observe this qualitatively, not quantitatively.
So you don't have any...
No, and I don't think it's relevant.
You don't think it's,
no, I don't think
relevant?
it's relevant.
When the surface tension acts against
the surface tension is relevant for us to have the instability.
Yes, I know that you said that
this is the main
surface tension acts against creating fingers. I understand that,
yeah.
that's good. But when you said it, there must be some critical flow rate to create fingers.
Sorry?
Okay, I repeat my question. You said that the surface tension acts against creating fingers.
Yes.
And
right.
You said that must be a sufficient pressure to create the fingers. So now I want to ask.
We need to have a sufficient pressure for us to break the inertia of the liquid.
And
so
what was the sufficient pressure? The critical flow rate. I want to ask.
I have not calculated it because I don't think it's relevant. It's qualitatively relevant but not quantitative.
What was... What about constant flow rate and constant velocity? Because I saw that you pushed.
This was only a demonstration of the experiment.
Okay.
We used a weight.
So what was the experimental setup when you said that there was constant velocity, but I saw in the video that you pushed it by hand.
This is only an illustrative movie. steering wheel.
It's 1 kilometer. It's 1
kilogram.
It's 1 kilogram.
Yes.
Did you change the parameters of it?
No, we kept it constant for us to
When you have only 1 kilogram, you have a constant pressure.
Yes,
But
I have a
not
constant
constant
pressure here. So for the equation I use it, I have a constant flow rate. So the gradient of pressure along the radius parameter is constant. So I could approximate those velocities to a linear tendency.
I want to ask, in your solution, I didn't see the different distance of the plates.
Oh yes, it's here.
Can you show me the results?
Right. Here it is. Variating the distance between the plates, I have this tendency of the graph. And we can also calculate the average velocity. And
But I don't see the creating fingers. It depends on the distance.
oh, I calculated the velocity. That is what I can compare to my theory.
Okay, then explain me when, for example, the distance of the plate was 5, or what is it?
5 millimeters.
5 millimeters. What was the fingers?
The fingers, wrong. The fingers were small. They had a lower distance, a lower length, and but the separation between them and this divided by this was basically the same as when we have other separation of the plate, because it does not depend on the separation, only depends on the difference of the color.
So you said that when the distance between gap when it's very big distance, then
not very big. We cannot have a very big distance, but because we cannot approximate this to a Herschel flow, because we need this distance h to be much smaller than the distance of the plates themselves.
How big the gap between the plates must be to be the Herschel cell?
We need to have h very small, much smaller than the length of the plates. In our case, we use it from 0.01 meter to 0.4 meter. So it is much slower, much smaller. This is because when we have the minuscule shape, we can approximate this to a symmetrical one. But when we have a very big separation, the minuscules will be like this. So we cannot make the same approximation, and we will have a different mathematical model for it. So we could not approximate it to a Herschel flow. When you have the 6 and more millimeters, this velocity is different. It has a different behavior, not the linear test.
If the gap is what was the parameter of the gap between two plates when there was no grading of fingers?
It was 1 millimeter.
1 millimeter.
Yeah, 1 millimeter.
So it was very close to each other, and there was no fingers.
No fingers, because we were injecting more viscous fluid in a less viscous fluid.
No, I'm asking when you were changing the distance of the plates, and you observed a creating of fingers.
Yes.
I want to ask, and you said to me that with increasing of the gap, there will be bigger fingers. But now you said that
no,
with
not bigger fingers, smaller fingers, because we have a lower velocity.
So if I understand it quite good, you said that the gap between two plates, when it's smaller, so there will be no fingers.
No, I didn't say that.
No,
Okay,
I
the
didn't say that.
discussion time is up.
Okay.
I didn't say that.
You summarize your discussion.
So I'd like to conclude my opposition to the reporter. The parameters that I was asking was in the discussion several times changing, and I'm quite confused because maybe if you heard it, she said to me that when increasing of the gap with the gap between the distance between plates, there will be bigger fingers. But now, in the last minute, when I asked it, she said to me that when the distance between gap will be only 1 millimeter, there will be no fingers. I think that's not possible. I think when the distance between the plates is bigger, it will have influence of the creating of the fingers. So I think it was quite rushed and quite. Thank you for attention.
Reviewer, your time for questions. Reviewer, please, your time for questions.
Can you show me again the equation for the continuity of the flow?
Sure. Yeah, this one.
About the second equation, is it a typo or missing P or?
Sorry. Yeah, it was a mathematical error. It's missing a P right here. Sorry.
Okay. How can you be sure that the constant weight of the added mass that ensure constant flow rate?
This is only a first approximation because we could have variation of the viscosity with the velocity of the flow. But in the case we use it, and as we show it by the experimental graph, we could see that this flow rate was basically constant. So it's approximately constant. I only wanted to control the pressure, not the flow rate. So you could have a constant gradient of pressure approximation value.
What do you mean by the average velocity of fingers?
I calculated the finger velocity. Let me draw it. I filmed the finger flow, and then there were a few fingers. So I calculated for 3 fingers in medial point, and I measured the position of the finger and in the interval of 1/67 each finger. So I calculated the position.
Okay. So you have shown the fitted graph that the velocity is function from reciprocal of the h.
Yes, it's proportional to h squared.
Okay, time's up. Thank you.
First, I'd like to say sorry again for the time elapsed. I had some problems with the slide passing, and I'd like to explain better. I think there was a misunderstanding from the opponent team that I said when we have a more viscous fluid being injected, we don't have the finger pattern, and that was a distance of 1 millimeter. And this can be clearly seen in our experiment. And we always we have the finger formation when we have less viscous fluid being injected in a more viscous one for any distance we measure. The problem says to analyze the pattern. Yes, I did analyze it, and I made some conclusions and the cases and the relevant parameters. The flow rate that the reviewer talked about and the opponent as well, I can say that it could not be measured with our experimental setup because it was too difficult to measure because we have different, the instability varies, so the flow rate also varies. So we had the pressure constant, that was the most constant thing, the constant thing we could make. The physical explanation and the correlation to the experimental data was that we can, when we have a constant gradient of pressure or approximately constant, we can have a linear tendency for the position. So we have a fit to the constant velocity. And I think the reviewer have a misunderstanding on the random walk does not make the fingers longer.
Okay.
It makes,
Thank you.
thank you.
Joris, do you have questions?
Can you explain exactly, I saw your experimental setup where you have a mass kept on the top. The syringe, you're pushing it.
Yes.
Is it a constant mass you kept for all the liquids?
Yes, I kept them constant in order for us to analyze the patterns and compare them.
Do you think when you start compressing, the spread will be more or?
When I start compressing, first we have to break the inertia of the liquid. So this flow rate is a little bit smaller than the average flow rate during the experiment.
Go back to your formula of each flows. Flow square P over.
This one or
Yeah, what does that P stands for here?
the pressure.
And X?
X is the position. We consider it a Cartesian model.
Okay.
I have a question for the opponent. The reporter keeps insisting that he can calculate the flow rate because it's copying your experimental setup. If we have the same experimental setup like her, can you estimate the flow rate, or if you can't, how?
Can I tell my solution?
Yes, it's okay.
My solution was that I used two beakers, and by different height, I was able to calculate or able to control the pressure and the flow rate by hydrostatic pressure.
Okay.
Draw an analogy between this effect and this diffusion limited aggregation of solid particles or the crystal growth. So the other effect is the same. Is it only the visual analogy, or there is something deep? For example, it's described by the same laws or some mathematical relations?
Yes, we have the related mathematical analysis because in the three cases I showed, the crystal formation, the flat flow, and the bacteria growth, we have the random walk. And as you can see from the comparations and our mathematical formulations, this is the main cause of the finger shape. So I showed those images in order for us to see that as we have the same relation of the random walk, and this causes the finger.
Have you ever tried to estimate the fractal dimension in the phenomenon?
I didn't.
What is Darcy law?
Hmm?
What is Darcy law?
Darcy law is when we have the flow in a porous medium, and we calculate the velocity, and this is directly derived from the Navier-Stokes law. So it's basically they have the same parameters.
Any other questions? Okay, no. Okay. Please.
Okay,
Oh,
just
one more.
one
All right.
last question.
Yeah.
Can you give a reference to the source for your comment about Darcy Flow? Is it an article or a book? Just state briefly. Which one? Number 4? Is it a
Yeah.
book or an article?
It's an article.
Where?
One, it's actually the article. I have this.
All right. Okay.
It's an article.
Okay. Please. Any other question? We have some time left. No more questions? Okay, good. Please calculate the score.